Ladies and gentlemen, good morning or good afternoon or good evening. We are moving to the third part of this class, which is mathematical programming. And this lecture is going to be the first part of that third part, and that's going to be about linear programming. Okay, so linear programming, what we're going to do in the lecture is first find out what is a linear program, and then talk about convexity and geometry. Okay, so let me give you the context here. So linear programming was invented by George Dantzig in 1947. And it's one of the most fundamental tools in combinatorial optimization. It's one of the it has been a growing area for decades. And actually, people are still working very actively in this. And as I will tell you, there are still some very interesting open issues in that area. But the really important thing for us is that this is a really fundamental tool for doing a lot of different things in optimization. Okay. The other things which is very nice in linear programming is that you have these two views. You have the geometrical views, you have the algebraic view, and there are beautiful connections between them. So we'll switch typically from the algebraic view to the geometry view, and so on and so forth. And today mostly we'll talk about the geometry, but the next lecture is going to be about linking the two things together. Okay, so fundamental tools, beautiful connection between visual, geometrical intuition, and then the algebraic expressions of the problem. This is what a linear program is. Okay, so what you see at the top is basically minimizing a linear objective function. Okay, subject to a set of linear inequalities. Okay. Now, one of the things that you have to see here is that the variables will have to be non-negative, all of them. So in this expression, okay, so the xi are the variables, okay, real numbers, and the ci's, the ai's, and the bi's are the constant. Okay. So on this particular expression, obviously, you have n variables, you have m constraints. Okay. The variables, as I said, are non-negative. They have to take a non-negative value. Okay, and all the constraints here are inequalities. Okay, so that's the basic form of a linear program. Okay, so when we think about linear programming, we think about this. Okay, minimizing a set of a linear objective function subject to a set of linear inequalities. Okay, so here are the answer. Can I maximize? Yes, you can. Okay, so the way you would do that is simply by replacing the maximization of your linear objective by the negation, the minus of that particular objective, and you will minimize that. Okay, so if you minimize, minus your objective function, okay, so you will, in a sense, maximize. So if you want to maximize, just minimize and negate all the coefficients of your objective function. Now, can a variable xi take both positive and negative values? Can you actually represent that? You can, okay? And here is how you do it. You take variable xi, and everywhere inside your linear program, you replace it by a difference of two variables, xi plus and xi minus, okay? So essentially, you take this term here, and you replace xi everywhere by that particular term. Okay. Now, why does it work? Okay. So both of these variables have to take non-negative values. Okay. That's that's what a linear program does. All the variables have to take non-negative values. But when you look at this difference can take both positive and negative values. You want a positive value, give it to xi plus. Okay. And the other terms can be 0. You want a negative value, give a positive value to xi minus, a 0 to xi plus, and you get a negative value. Okay. So in a sense, very easy, right? So you have a variable, it can take both positive and negative values. What you do is you replace them by this term everywhere inside the linear program. Okay? Now, what if you have inequality constraints? Very simple as well. You take that equations, you replace it by two inequalities. Okay? In one smaller equal, one greater equal. The smaller equal, you can you just transform it into a smaller equal as well, and you have essentially an equation at that point. Okay? So very simple. Okay? Now, what if my variable can take integer value? That you can't do in a linear program. Okay? So this is something that we'll talk about later in the class. Okay? It's going to be what we call mixed integer program, but this is not a linear program. And you'll see there is a fundamental difference between these two. Okay? Now, what about, if I have a nonlinear constraint? Okay? Well, what we are talking about here is a linear program. It's not a nonlinear program. It's called a linear program for a reason. We only want to have linear constraints and linear objective function. And that gives me the opportunity to tell you a story about George Dantzig, of course. When George Dantzig presenting this, he was invented linear programming. He was a graduate student, and when he wanted to present these results, he went to this conference, and there were plenty of, big shot in optimization there. And so he presented his results, okay? And then there was this big shot in optimization, this big German guy with a big deep voice, right? And so he stood up and said, Mr. Danzig, you very well know that the world is non-linear, okay? And so Danzig was like, shaking up a little bit. Oh, am I going to answer that question? And then, at that particular conference, John von Neumann, the genius in computer science and applied mathematics and mathematics in general, was there, and he stood up and said, Mr. George Danzig stated his axioms, okay? He told you when you can apply, the method. If you have a problem that fits in the method, use it. If your problem doesn't, don't use it. And I think, that was really classy, and I'm sure, George Danzig appreciated that a lot. Okay, so essentially no linear constraints, no variable that can take integer value. That's outside the scope of linear programming, okay? The rest here you can express essentially, the way you want. Okay? Now, let me talk about geometry, right? So we just saw the algebraic form of what a linear program is. So I want to talk a little bit what this means from a geometrical standpoint. And so I'm going to start with convex sets, okay? And so I give you a couple of sets here, okay? A set of points, like, the points inside a circle, inside a square, inside this, kind of apple, square where, the corner are rounded, right? And then this part is this star, okay? So which one of these are convex sets? Okay, so the intuition is very simple. Take 2 points, draw a line between them, okay? If all the points between these two, if all the points in the line between them are inside the set, okay, that means that the set is convex. Okay, this is convex, okay? We are happy, okay? So this is the star that I'm showing. Let's take 2 points. Let's draw a line between them. What do you get? There are some points here which are outside the set. Therefore, this is not a convex set. Okay, not happy. Okay? No, this is 2D. 2D is really boring. So let's move to 3D. Okay, and this is 3D. Okay, so you see this sphere. Okay, it's a convex set. Okay, you take the 2 points, you draw a line between them, and look. Whatever you look at it. Okay, all the points in between these, all the points in these lines are inside a convex set. That's what a convex set is all about, okay? So let's move to the next one. Okay, here is the next one, okay? So you see this thing? It looks like a convex set, right? But look at this line. I selected 2 points. I drew the line between them. I go to sit. Whoops! You see there? You can see clearly, the lines goes outside the set. This is not a convex set, okay? So beautiful thing here, okay? You can look, you take 2 points, you draw a line between them, it's outside the set. That's not a convex set. Okay? So this is, once again, the geometric intuition. What I want to show you now is the algebraic expression. Okay? So if you set a point V1 to V1 to Vn, okay? So we will define the convex combinations of these points. And the way you define this convex combination, and that's essentially the points which are on this line, right? So but of course in arbitrary dimension. Okay? So what you do is you multiply every one of these points by these lambdas, lambda 1, lambda 2, lambda n, if you have n, points. And that's going to be a convex combination of all these points, V1 to Vn, provided, of course, that the sum of these lambda is 1, and they are all greater or equal to 0. Okay? So if I have an expression like this, okay, and I make sure that all the lambdas are equal to 1, and all of them are greater or equal to 0, then I have a convex combination of the point V1 to Vn. Okay? So this is how I can define a convex set. Okay? So why? Because essentially now a convex set can be defined in the following fashion. So you say a convex set, okay? A set essentially is convex if you take points of these things and all the convex combination of the points that you have in the set are inside the set. Okay? So you basically take a bunch of points. Okay? These points are going to be for convex if whatever convex combination you take, those points are inside the set. Okay? So that's a convex set. Now, so this is an interesting result that we're going to use all the time. Okay, so essentially, the intersection of a set of convex sets, okay, is itself convex. Okay, and so this is the proof. Okay, it's a very, very simple proof. So let's denote by this notation here the intersection of all the set Si. Okay, from 1 to n. Okay, so we take this intersection of all these sets. Okay, and of all the set Si, right, that you see. And so what we're going to do is we are going to consider, okay, a bunch of points inside this intersection. Okay, so let's say V1 to Vn are the points inside that intersection. Okay, so what it follows, obviously, because they are inside the intersection, that basically means that they are inside every one of the sets. Okay, so the points inside the intersection, by definitions, are inside every one of these sets. Okay, now, what do we know about the sets? We know that the sets are convex, okay? So essentially what that means is that all the convex combination of these points are also in the set I. And that's valid if it is S1, S2, S3 for all the sets, right? So now what do I know? I know that every convex combination of these points are in every one of the sets. And therefore, they are in the intersection of the set, okay? And of the sets. And that means what? That means that essentially all the convex combinations of the points inside the intersection are inside the intersection, and therefore the intersection is convex. Okay? Now, why is this interesting? Okay? So look, when we look at linear programs, we have these inequalities, right? And these inequalities, okay, so they are basically representing half spaces, and these half spaces are convex. You can prove that. Take the definition that I've shown you before and try to prove that this is convex. And the proof is very simple, right? 3 lines. Okay? But you can prove essentially that every one of these half spaces are convex. And so when you look at the linear programs and the constraints of the linear programs, what you have is essentially a bunch of these half spaces that are defining the feasible region of the linear program. And so all of them, are convex, and the intersection of them is also convex. Okay? And so this is called a polyhedron, okay, the intersection of all these half space. And if it is finite, that means it doesn't go to infinity in one of the dimensions, it's called a polytope. Okay? So big idea here is what? We are dealing with convex set. Every one of these sets every one of these inequalities is basically defining a convex set, which is called a half space. You have many of them, so for having a solution, you have to satisfy all of them. That means that you have to be in the intersection of all of them, and I told you that the intersection of a set of convex set was convex. And therefore, we know that the intersection of these things is going to be convex. Okay? So let's look at these things a little bit geometrically, right? So this is an hyperplane. Okay? So this is an hyperplane, and that defines a half space. And let's assume that, we are looking at the solution on this side. That's part of our feasible region. Then I can take another one, right? So I take another half space, okay? And I, refine my feasible region. And the little guy over there, that's called a vertex, okay? And you're going to see today, I'm going to really be obsessed with these vertices, okay? But that's another one. I can take another one, and then the colors are getting uglier and uglier and uglier, but I'm getting this intersection of these sets. Actually, I don't really know if they are, ugly because I'm colorblind. I don't see anything here. But anyway, I was told that they are really ugly. So we're not going to represent them. We're going to represent the feasible region like this. So this is essentially all my hyperplanes. They are defining half space everywhere. Okay? Think of them as inequalities. And then this is the feasible regions of the linear program. Okay? You see the algebraic version of every one of the inequalities that I've been mentioning here. Okay? So this is in 2D, right? So it's boring. So we're going to see 3D as well in a moment, right? But before that, what I want to do is telling you a little bit more definitions here. So a face, okay, we'll talk about face and facets. So face is basically the intersection of finitely many hyperplanes, okay? And so if we are in dimension n-1, we'll talk about facets. And this, you'll see later on why these facets are important. Not right now, not really for linear program, but later on they will become very important. And then of course, when you are in dimension 0, you will have what we call vertices, okay? And you're going to see I'm completely obsessed. Today I'm going to be really obsessed with these vertices, okay? So this is in 3D. Okay, so this is the first hyperplane we see here, okay, a single hyperplane. And we're going to increase the number of hyperplanes up there, but you see the first one over there, right, in 3 dimensions. Okay, and now look at this. This is 2 hyperplanes, okay? So you see, the top and the mostly vertical and mostly horizontal hyperplanes. You see now that these 2 hyperplanes intersect. The intersection of these 2 hyperplanes is a line. Okay, you see the line clearly over here. Okay, and now this is the really beautiful part. Okay, so you see these 3 hyperplanes now. Okay, so when 2 of them meet, you have these lines that you can see. Okay, here, over there. and of course, when all three of them meets, you get this unique point that you see at the back of the picture there. Okay, so that's essentially what you get when you have a finite intersection of this hyperplane. Okay, in 2D, when you have 2, you have a line. When you have 3, you have a vertex. Well, you have a point. Okay. Okay, so what you see on the screen now is a huge number, not a huge number, a nice number of hyperplanes, and you get a very nice polytope that you see over there. Okay, so you can see all the facets, you can see all the vertices, you can see, this entire polytope, and that's essentially the kind of objects that we are going to manipulate inside linear programming. Okay, so we have this polytope, okay, nice polytope, and we add a new hyperplane. Okay, so you can see the new hyperplane. It's going to intersect with that polytope. Okay, so that's what we want to look at here. Okay, so you have the polytope, we have a new hyperplane. Okay, that's a new constraint in your problem, right? And so what's going to happen? And this is what happens. Look at these new polytopes now. We have a new facet, okay, and a bunch of new vertices here that you can see. This is from the top, this is from the side, okay. So all these, so that what this hyperplane did was cutting through the polytopes and then adding a new facet, okay, and then adding a couple of new vertices as well, okay. Once again, what you see there is basically what all these, hyperplanes are creating, and they are creating these beautiful polytopes with a bunch of facets and a number of vertices here. Okay. Now this is a very important result. Okay. So every point, okay, inside the polytopes, the polytope that I've just shown you, which are defined by these hyperplanes and half spaces, is a convex combinations of the vertices. Okay. So that's a very interesting result. That basically means that every point inside this polytope, right, can be expressed as a combination of the vertices. I have this point here, okay, it's a combination of these two vertices. I have this point, it's a combination of these three vertices here, okay? So that's a very interesting result, and we're going to use it for, actually proving some very interesting results in the theory of linear programs, okay? Now, why am I so obsessed with these vertices? And this is the reason why. If you have a nice linear program that as I have shown you so far, okay, what you know, okay, is that at least one of the points where the objective value, this guy here, right, is minimal, okay, is going to be at a vertex. It doesn't mean that, there are no other points where the solution is optimal, okay, but there will be at least one of them which is located at a vertex, okay. So in a sense, that's why we are obsessed with these vertices, right? So because we know that at least one of the optimal solutions, okay, is going to be at one of these vertices, okay? And I'm going to show you the proof, okay? But essentially, so let's look at it in a geometric way, right? So this is an hyperplane, right? So I'm basically saying, I take the objective function and I assume that it's equal to a particular value b, okay? That defines an hyperplane, and you see this hyperplane here, right? So what I'm trying to do, in a sense, is minimize that b, right? So in a sense, I'm trying to take this hyperplane, okay, and bring it down, okay? And so this is what we're going to do, okay? So when we optimize, we get to a particular point where this value for b is going to be minimal, and so this is a point that you see over there, and that point is on a vertex, okay? And we're going to call it B star. And so you'll see optimal solutions are always going to have a little star in these lectures, okay? So in a sense, once again, we took that hyperplane and we tried to minimize the value of B because that's the value of the objective function. And so we move that hyperplane, and when it's minimal, you can be sure that at least one of these points is a vertex. So once again, we take this thing, we bring it down. It's beautiful, okay? And we have the optimal solution there. Now, this is boring, okay? So let's do it in 3D. And now, ladies and gentlemen, the 3D version, right? So what you see there is more beautiful polytopes, and you see this hyperplane there, which is defining the objective function, okay? And what we are trying to do in this one is maximize, okay? So we're going to take this hyperplane and do exactly what we did in 2Ds, right? So at this point, it is equal to a constant, and we are going to try to drive it towards one of the vertices of this polytope. And this is the result, right? So you see this hyperplane now, and you see it intersecting finally with this polytope, okay? And this is probably the best angle here, right? So you see that? It's intersecting with that vertices, okay? Everywhere else, it doesn't touch the polytope, okay? And so this is also very nice, okay? So you can see that now this objective has been maximized, and it's basically at the particular vertex of this polytope. So I told you, that at least one of the optimal solution is located on a vertex, and this is the proof, okay? So it's a beautiful proof, very simple proof, okay? And that's why I want to go into it. It's something that you can understand inside the lecture, okay? So let's go about x star, which is the minimum value. That's where, that's where the linear program is optimal, okay? This is a point somewhere, okay? And we assume that it's, we basically, this is the optimal value. This is one of the optimal solution, okay? Now we don't know where this point is, right? So we want to show that it's on a vertex, right? So we take that point, okay? And we know that every point inside a polytope can be expressed as a convex combination of the vertices, okay? So let's assume that these vertices are V1 to Vt. We can re-express x star, okay, this optimal point, as a convex combinations of these vertices. And we have this, this lambda 1, lambda 2, lambda n, lambda t, and we know that the sum of these lambdas has to be equal to 1. We're going to use that information later on, okay? So now the objective value at optimality is c times, x star, the optimal solution, and therefore, we can re-express it in terms of the vertices and the lambdas by simply multiplying that, right-hand side by c. Okay, so we basically have at that point that Cx star is equal lambda 1 times, C1 times C times V1 plus, the same thing for the other vertices. Okay? And so at this point, we just have done, some very simple, algebraic manipulation, knowing that every point inside the polytope is a convex combination of the vertices. So what I'm going to do now is assume that this point, this x star is not at the vertex. Okay? And I'm going to assume that is not a vertex. So what I'm assuming essentially is that Cx star is always smaller than C times Vi, okay, where Vi is one of the vertices. It's going to be smaller than all of the vertices, okay? And what I'm going to do is derive a contradiction, of course, okay? And that will prove that it has to be at least on one of these vertices, okay? And how do we get the contradiction? Well, let's start with Cx star. So we start with Cx star, okay? And then we simply rewrite, the formula that I showed before. But now at this point, you see CV1. What do? Well, we made the hypothesis that Cx star was smaller than Cvi. So if we can replace every one of these Cvi, okay, by Cx star, and we know now that Cx star is going to be greater than that because I'm replacing every one of these components by something which is smaller, okay? Now I factorize the Cx star, okay, and I get the sum of the lambdas and Cx star. I know that because this is a convex combination that the sum of the lambdas are equal to 1, so I get Cx stars. So what I get is the formula, is basically the contradiction here. I have that Cx star is greater than Cx star, which is really difficult to do, right? And therefore, one of the hypotheses that I took, was wrong, and this is the hypothesis that the value of the objective was, smaller than all the vertices. So I know that essentially, the optimal solution has to be on a vertex, okay? Very simple proof, right? So at this point, so we know we have a lot of information, right? So we know that the solution of a linear program is located to one of these vertices. Okay, so now I have a geometric algorithm to do that, right? I can solve the linear program geometrically. I just draw this polytope, okay, and then I enumerate all the vertices. For every one of them, I compute the value of the objective function, and that's going to be giving me the optimal solution. Okay, so that's the algebraic view. Okay. So what we're going to do next time is to show how this geometrical view can be translated into an algebraic view, which we will be able to solve in a little bit easier fashion. Okay? Thank you.